Thank you. Right, so as you can see, I'm with the UCLA Office of Advanced Research Computing, otherwise known as OARC. I am joined today by Andy Lin and Siavash Jalal, and they are going to be addressing any questions that are put into the chat. Now, we're a fairly small group, so I would say if you're comfortable with it, please just unmute yourself and ask questions as we go along. And that's perfectly fine with me. Somebody might have to break in and tell me that there's a question, but you know, I'm totally fine with questions as we go through. Do not panic about the fact that there's 140 slides, okay? I know that's the first thing that people look at and they go, oh my goodness, what have I got myself into? The reason that there are so many slides is that I put the process output on the slides and I broke it up into usually about 6 slides for the output so that the output wouldn't be microscopic. For those of us who are a little bit older, small printing is something of a problem. And so at least for my own benefit, I can't have super small type. So don't panic about the number of slides. It's just that the output got broken up across numerous slides, although I will be showing you and running this stuff live as well. I'm not going to be able to go into presentation mode with the PowerPoint slides though, because when I do that, I can't see my tray to bring up SPSS when that part is necessary. So without further ado, let's get the show on the road. Okay, so we're only going to cover some of what can be done in the process macro. Andrew Hayes has written this wonderful macro for SPSS, SAS, and now R, and it does, in addition to moderation, which means interactions, it also does mediation and moderated mediation. So we're just kind of touching the tip of the iceberg of what this macro can do. We're using version 4.0 of the process macro, and that can be found at the website listed here. I'll show you that in a second. And much of the material from this workshop is based on his book. It's the 3rd edition of the book, 4th version of the macro, 3rd edition of the book. Let's see here if I find my, so we'll get to this in a second. Here's the homepage for the process macro here. And so you can see there's all sorts of stuff. And this is where you'd click to go to the downloads, and it explains how to download everything. And then this is the link to the book. As I said, it's the 3rd edition of the book. Now, these two are very much linked in that there isn't a lot of documentation for the process macro outside of the book, because Andrew Hayes's purpose is for you to buy the book so that you can use the macro. So if you find yourself having difficulty getting the information you need to run the macro, that's kind of to be expected, because the whole thing is that you're supposed to buy the book, and the book's got all the information that you need to run the macro, in addition to a bunch of other really great stuff. I really recommend this book because it's got a lot on interpretation in the moderation, in the mediation, in the moderated mediation, and all of these sections. And, you know, everybody struggles to make sure that they're running their model. But when you get to the interpretation, that's really where the magic is. And so having a good source to tell you what to say and what not to say, because that's almost as important, well, that's the real magic, the real gold. So this is the book. Most of today's talk is based on this book. And in fact, for a lot of things, I have page numbers as references for folks, because I certainly find that part to be helpful. Let's see here, that's this. If you installed Process before coming here, then you can run the examples along with us. If you didn't, don't worry about it. That's perfectly fine. You'll still get plenty out of the workshop. And I do have a bunch of examples that use native SPSS commands. So you can certainly run those in SPSS and everything will work fine. The important thing to remember about process. So as you know, with SPSS, there is a syntax that you can use, and there's also the point and click interface. And Andrew Hayes has followed in that tradition. There is a point and click interface for process as well as the syntax. The trick is that when you install the point and click interface, it's installed once and done, and that's all good. But every time you open SPSS, you need to run the code to launch the process macro. So don't open SPSS and start putting variables in the process point and click dialog, because it's not going to run until you've run the macro. And once you've run it, it will be usable until you close out of SPSS. And then when you reopen SPSS, you need to just run the macro again. All righty, so you can get the data sets off of the web page. This is the web page for today's workshop. That's the link to the process macro page that I showed you, and the link to the book. Here is the link to the PowerPoint slides that I'm going to be using today. So you've already seen the first 4 of those, so that's where this is located. We're using 2 example data sets, HSB moderation and exercise. So you can download those. I recommend you save them in a place where you can find them easily, but whatever works on your own computer system. There is a syntax file that I'm going to be using. You can download that right here. And then some of the slides have a title of try it yourself. So we've got some questions, some exercises, things for you to try yourself. And here is a text file with the answers. I'm going to ask you not to look at the answers until the end of the workshop, just so that, you know, we can have some conversations and talk and try some things out. But here are the answers in case that's helpful for you. All right, let's go back here. Let's see here. Oh, for some reason in SPSS version 28, the command or the option to have the commands echoed in the log file or the output file somehow got turned off. And if that's true on yours, you probably want to turn that back on so it will echo the syntax. If you need to do that, come here to edit. It doesn't matter what window you're in, and then come to options and then look under viewer, and you want to click display commands in the log, click on apply and click on OK. And then the commands will show up in the log file, and you'll want that record of the commands. So we got that. So let's start getting into some real content here. Definition of an interaction term. What is an interaction term or a moderation term? Interaction terms, they're very common in regression, but without them in any sort of regression model, the effect of one of the predictors on the outcome is independent of all the other predictors in the outcome. In other words, you more or less just got parallel lines going on here. And for a lot of models, that is sufficient, but for perhaps even more models, that is not sufficient. And what you're saying to yourself is, wait a minute, the effect of predictor A on my outcome depends on the level of predictor B. Likewise, the effect of predictor B on my outcome depends on the level of predictor A. When you start having that conversation with yourself, when you start hearing yourself thinking, wait a minute, these two things, I got to know about 2 variables in order to know what's going to happen to my outcome, you've said interaction, all right? And so the interaction term is the product of those 2 predictors. Literally, you just multiply the 2 variables together. Now, in process and in some of the procedures in SPSS that we're going to look at, you don't actually need to do that multiplication. The algorithm will do it for you, but that's functionally what is happening, is that the 2 things get multiplied together. So this inclusion of this interaction term means that, as we said, just the level of one predictor on the outcome depends on the level of another. Okay, that's good. They're symmetric. We talked about that. So we've got that. And now for simplicity, and this is true in the Hayes book as well, some authors refer to one predictor as the predictor and the other as the moderator. The important thing to remember is that those are names that are used by human beings. Okay, they help people, but there's no difference mathematically between your predictor and the moderator. You don't specify them. One is the predictor and one is the moderator, or anything like that. The algorithm thinks they're all predictors, right? So those are terms that humans use, but it's not terms that the software uses. So don't get that part confused. So in this workshop, you're going to learn how to interpret the coefficients of the interaction terms and the lower order effects. We'll explain what that is in just a minute, and how to probe the interaction and how to graph it. Now, a lot of researchers find that the interpretation of the coefficients of the interaction terms is really difficult. And honestly, the readers of journal articles find the same thing, that the interpretation of the interaction coefficients is very difficult. So it's a lot of folks just report whether or not the interaction term is statistically significant and then present the graph of the interaction and then go on to discuss the meaning based on the graph rather than the regression coefficient. Now, I want to pause here for a second. At various times I will talk about statistical significance, and I do acknowledge that there is quite the discussion around the overuse of significance tests and what they really mean, if they mean anything at all. I'm not going to journey into that realm in this presentation, but I do acknowledge that it is there, and some of my use of p-values here may seem, I don't want to say a bit out of date, but may not be where things will be headed, say, in 10 years. But honestly, I don't know where things are going in 10 years, so maybe not, I don't know. The SPSS procedures to run linear regression. There's a bunch of them. I did a presentation, forget when it was, and I counted up, I think it was something like 18 different procedures in SPSS that could be used to run everything from a t-test to a linear regression. Some of those include the regression command. Boy, surprise there that the regression command runs regression. GLM, mixed, and the SPSS command linear. However, most of those procedures lack the ability to graph the interactions, and that is one of the big weaknesses of SPSS, in my opinion, because, like I said, interpreting those coefficients is tough going. And even if you do interpret it correctly, there's really no substitute for seeing what that interaction looks like. One exception to this, though, is the GLM command, which can graph binary by binary interactions. So, or I actually should have said categorical by categorical interactions. It can graph those kinds of interactions. But once you get a continuous predictor in there, then we're out of luck there. That's why the use of the process macro is so helpful, is because the process macro is going to give us SPSS syntax that will allow us to graph these interactions that can't be graphed by native SPSS commands. And so that's why we're here using process. It's not that I need process to run these models. In fact, for almost all the models, I show the SPSS syntax for it. It's the ability to graph it that we need process for. All righty. I already talked about all that, so we can move on from that. We've got two practice data sets. The first one we're going to use is HSB moderation. The outcome is a continuous variable called opinion. Predictors include continuous things like detail, age, I forget what the research question was for this. I didn't make up the examples to follow a research question or anything like that. I was actually looking more at what made for a good presentation for showing you interactions. So don't really worry so much about theory here, but in real life, of course, you would. The exercise data set we'll use towards the end when we get into continuous by continuous interactions. The outcome variable there is loss, basically weight loss, and predictors there include hours, effort, and a binary variable called female. A little bit of SPSS housekeeping here. We need to use the commands dataset name and dataset activate. And the reason we need to do that is because SPSS can have more than one data set open. As you can see down here in my tray, I've actually got 2 data sets open. I've got exercise and HSB moderation. And when you're using syntax, you have to tell SPSS which data set to run your code on, right? Because obviously, if I am running code that has opinion in detail and it's trying to work on the exercise data set, all I'm going to get is a bunch of errors. So these commands here, this data set activate in particular, is going to tell SPSS which data set to activate as we go through and execute the codes. The get file command is used to bring an SPSS data set into SPSS. So we start off with get file. That's just the path it's located on my computer. Obviously, you change the path to fit wherever it is on yours. And in the syntax file that we've got here, we have, here's our get file and data set name. Here's our get file, data set name, data set activate, so that we are working on this data set HSB. I just shortened it to HSBM here. And then when we go to execute this code, we'll be operating on the correct data set. All right, we're going to start off with the binary by binary interactions. That should be the easiest place to start. So that's where we're going to go. Let's scroll down here a little bit. Interaction in lower order terms. In our example here, our interaction term is going to be the product of 2 binary predictors. I called them binary var and bco var. Oh, I forgot one other thing. Probably is a bullet point I missed. SPSS allows for very long variable names, something crazy like 32 characters or something for a variable name. However, because of the way that the SPSS process macro is written, you really get into trouble if the variable names have more than 8 characters. And so in all of the examples, all of the variable names have at most 8 characters. So that's why it's not binary VAR, it's binary VR, because we had to keep it down to under 8 characters. If you're using the process macro, although there is a long names subcommand that you can use, the strong recommendation is to shorten all of your variable names down to 8 characters. Otherwise, you could get erroneous results because process is getting confused between the variable names, because especially if the first 8 characters are the same, then all bets are off. So keep the variable name short, and definitely make sure the first 8 characters are different. All right, so we've multiplied these 2 variables together. And these variables are also going to be included in our model. And those are the so-called lower order terms. All right, they have to be in the model so that everything is interpretable. And so in consequence, we've got 3 predictors. We have binary var, bco var, and their interaction. Do not use recoded versions of the lower order effects. What does that mean? It means that if I multiplied this variable by this variable, then that variable and that variable should go in the model as they are, as the way that they were coded when I did the multiplication. There's a warning in the book, and we've seen it in consulting, where people have recoded the lower order effects, and then the interaction was with the original variables, and that doesn't work out so well. So just make sure that, you know, when you multiply the variables together, then you left those variables as they were to go in as the lower order effects. Our conceptual diagram looks like this, and Hayes is really good about providing both the conceptual diagram and the statistical model. We have X predicting Y here and W, and see how it's pointing to the line here? That means interaction. Okay, so that's how you read this. We've got X predicting Y, and then we've got this interaction. That's the conceptual model. The statistical model looks like this. We have X going to Y, W going to Y, and X times W going to Y. In other words, we've got our three predictors here to predict Y. And so that's what that statistical model looks like. This is particularly helpful because now it's pretty clear on how you're going to write your syntax. Before we get to the process command, though, I'm going to show you how to do this in SPSS GLM. So I'm going to talk you through this syntax, and then we're going to go turn around and run it live. Okay, first things first, SPSS syntax is not case sensitive. You can type in uppercase, you can type in lowercase, any combination. SPSS does not care. All right, when you look at the SPSS syntax guide, they will by default have their commands and keywords in capital letters to distinguish them from elements that you need to provide, such as the outcome variable and the predictor variables. But when you're typing syntax, you can type in all lowercase. I certainly do. That's my preference. You do it however it reads best for you. SPSS syntax is like a sentence in English. It must end in a period. So do not forget the period, please, because if you do, you will get weird error messages, and none of it will say you forgot the period. So, you know, you could be tracking down, I don't know what, and never realize, hey, wait a minute, I just forgot the period at the end of the command. So this is the end of command marker. Don't forget it. I tend to wrap my syntax like this, but when you look at the process syntax, you'll see it all out on one line. Again, SPSS does not care. It's just for what readability for the human beings. Our command is GLM. Our outcome variable is opinion. This is the SPSS keyword by. SPSS has maybe half a dozen keywords. The two most commonly used are by and with, and they're used in almost all of the SPSS commands. The SPSS keyword by means that categorical predictors will follow. The SPSS keyword with means continuous predictors will follow. So if I wanted to add a continuous predictor here, I would just say with, and then put that variable or variables there. The trick is you only get to use by once and you only get to use with once. You don't have to use both of them. You can use one or the other. And the order doesn't matter. It doesn't matter if you put the by variables first or the with variables. In the SPSS point and click syntax, which I'm not going to show you, but if you were going to use that, what you would see is fixed factors corresponds to by, and covariates corresponds to with. So that's the relationship between the GUI and the syntax here. So all of the predictors get listed here, and then we have a design subcommand. SPSS has subcommands. SAS has statements, SPSS has subcommands, okay? We have a design subcommand. It is necessary, and you list the whole model out here. So lower order effect for binary var, lower order effect for covar, and then our interaction term here. We use the star to indicate multiplication. By default, the GLM command does not print the coefficients, the regression coefficients. So this print parameter will provide that for you. The EM mean subcommand, EM mean stands for estimated marginal means, is used with variables that follow the SPSS keyword by. And so if I want to use this subcommand, I have to use by here, and I can get the table for the interaction here. So I'll have a 2x2 table, and the contents will be the expected value of our outcome for each combination of these variables. And we're going to end with a plot subcommand, and we're going to plot the interaction and ask for the error bars here, and we'll ask for the standard errors as the error bars. By default, SPSS uses the highest numbered category as the reference group, and this default cannot be changed. Oh, I sigh every time. And the reason I do is this. If I have, I call them binary variable and binary covariate because they literally are binary. They are 0, 1 variables. In regression in most applications, 0 would be the reference group and 1 would be the comparison group. But because of the way SPSS works, 1 is now our reference group. So if I wanted 0 to be the reference group, I would change that to with, and I'll show you an example of that a little bit later. But then I lose the ability to use these two subcommands. And so there's no free lunch. What I personally end up doing when I do this kind of thing in SPSS is I run it both ways. And obviously they are the same model. The coefficients for the lower order terms will be different. That's a-okay, that doesn't matter. But that way I can get the output I want and the graph that I want. I just have to run it twice. All right, so this is the HSB moderation data set. This is what it looks like. I have an ID variable here. I have a continuous variable age. Here is my binary variable B covar. This is my continuous covariate, another continuous variable. Dummy variables that we don't need for this workshop. And then this detail variable, which is continuous. And then what I did here was that I made it either as a binary or as a trinary variable for examples later on. And then impact and opinion are also continuous variables, and opinion will be our outcome. So here we go. We've got all of this set up. Let's go ahead, highlight this and click on the big green arrow, and voila, we have output. Isn't that great? Okay, so let's talk through this output here, and the graph is down below. We'll get down and look at the graph in just a second. Let's go through this. Your first point of interest is usually this line here for the corrected model. And it tells you overall, is your model statistically significant? The answer here is no, it's not. In most research applications, the conversation would stop there and you'd say, oh, got to rethink things, got to go do something else because, you know, we've ended right here. For purposes of demonstration, I'm going to continue on. Nobody cares really if the intercept is statistically significant. The lower order effects are clearly not, and neither is the interaction. In cases where we have variables that each and have only 1 degree of freedom, the p-values from this table and this table are going to be the same here, but you think, why do I have this table up here? And this table becomes much more useful when you have variables that have multiple degrees of freedom, like that 3-level detail variable that I showed you. It would have 2 degrees of freedom. And so that 2 degree of freedom test would show up in the tests of between subjects effects. Okay. Looking down here, this is our intercept. We have this value for the intercept. This is for our, again, binary var equals 0, and this is the reference group. SPSS lists all this stuff out and then sets it to 0 because it's redundant. I think it's the only software package that does that. Most of the other software packages would not present these lines to you. And then here's the coefficient for our interaction term and our confidence intervals here. And then scrolling down here, this is the output generated by the EM mean subcommand here. These are the predicted values of our outcome given this model. And then SPSS was nice enough to graph it. Now, we see here what looks like a really nice crossover interaction. And this is partially why I selected this example, because if you look at the graph, you think, wow, I've got a beautiful crossover interaction. But the trick here was the inclusion of those standard error bars. And as you can see, especially for this here, they're huge. And both points are contained within both of the confidence intervals. And that's kind of the graphical explanation of why that interaction isn't statistically significant, because those lines actually could be parallel. We don't really know what they look like here. And so without those error bars, the graph could be a bit misleading. So I wanted to use those error bars there to show you that even if you do have what looks like a really nice crossover interaction, maybe it's not really there. Let's see here. I just copied the output right into here. Oh, hey, here's a question. We notice here that the p-value here is 1.47 and 0.913. And then when we look over here, we see 0.692 and 0.572. But the p-value for the interaction, let's see, where's the p-value for the interaction? That 353 is the same. Why is the p-value different for the lower order groups? Anybody want to tell me what? Pretty sure I know what that delivery is, but anybody want to unmute themselves and tell me why those coefficients are different? I'm sorry, I don't mean coefficients, my bad. Why are the p-values different between the two tables? Anybody want to take a guess? I hear silence. Oh, come on, somebody be brave, unmute, try it.
I'm brief and I'll read you what Michael's son wrote, which I think is the correct answer. The interaction is crossed over and the relation is inverse. Is that what we expect to see? So you have them going in different directions from baseline, from 0. And so one goes higher, one goes lower. And so net, they're that 0.3, but individually, those are the significance, I think.
Okay, I'm not sure I understood all of that, but in this table, 0 got used as the reference group, and in this table, 1 got used as the reference group. And so what we're looking at here are simple effects, and this is the simple effect here when this equals 0. Likewise, this is the simple effect when binary variable equals 0. And here, there's the simple effects, but for the other groups. And so that's what that whole thing was about. Yes, it has to do with the coding of the variables. So I've got lots of slides on interpretation because, like I said, that's kind of where the magic is. So let's talk about interpretation here. We discussed that the overall model is not statistically significant. You'll notice that the R squared is very small, which you would kind of expect given that the model isn't statistically significant. In the output here, you would see the R squared and the adjusted R squared here. Okay, when you say the adjusted R squared is 0, you kind of know you got to go do something with that model because that's not good. All right, let's see here. We've got all that. The interpretation of the intercept, aka the constant, the two words that mean exactly the same thing in statistics. It's the expected value of the outcome variable when all of the predictors in the model are held at 0. In this model, that's a reasonable value for both predictors because they're coded 0, 1. However, in lots of models, 0 is not in the range of 1 or maybe even any of the predictors. And so interpreting that intercept doesn't make any sense. You report the intercept. You must report it so that somebody could like actually write out the regression equation, but you don't interpret it. Okay, and throughout this workshop, we're going to make a distinction between reporting something and interpreting it. And so this is the first instance we've come across here where we have said, hey, look, I need to report this. I need to tell you what the value is, but I'm not going to interpret it because in some sense, sometimes it doesn't make sense. If you want to interpret it here, then you may do so if it is important or meaningful in your research. So for example, if the zero category, the combination of values 0, 0, if that's an important number for you, then that's great. If in your research question it's like, who cares? You still report it. You don't need to interpret it. Let's see here. This is the coefficient for our binary variable, and it's the effect of the binary variable when B covar equals 1, because again, couldn't change that coding there. The coefficient is negative, so it's got a negative or reverse relationship with the outcome. So as one goes up, the other goes down. Given this model, okay, I don't want you to think that that means that's the way it is in reality for all time and all models. No, just for this particular model. If you respecified this model, that coefficient may become more negative, it may become positive, it could do whatever it's going to do. So only within the context of this model is there a negative relationship between that predictor and the outcome. So we would say that for a 1 unit increase in binary variable, the expected change, or in this case decrease, is approximately 1 unit, right? This is a decrease. I'm going to call that 1 unit. You can call it 1.1 if you want, holding all other variables in the model constant. And it doesn't matter where you hold them constant. Because there's only 2 values for a binary variable, you can also say the difference between the groups is approximately 1 unit when B covar equals 1. In practice, I would not actually interpret it because it's not statistically significant, because it could actually be 0. I don't know, but that's the interpretation that you would have. We stated that always need to report every coefficient, but it is your decision as the researcher whether or not you're going to interpret it. I've actually seen a number of research papers where they've had this huge table of coefficients complete with interactions, this, that, and the other, and the researchers have chosen not to interpret any of the coefficients and instead moved on to interpreting predicted values or interpreting graphs. And that gets published. That seems to be quite acceptable, excuse me on that. So there's some flexibility here, all right? But what I want you to have is a set of good resources to go back to when you have to interpret something, because it's always very technical and you don't want to mess that up. And so it's written here whenever you need the information, come back, literally just substitute in your own variable names and your own coefficients and you're good to go. All right. Coefficient for B covar is 2.167. This is the effect of B covar when binary var equals 1, not statistically significant, difference in the group coded 0 and 1. Both of these are called simple effects or conditional effects. Hayes calls them conditional effects. I see the term simple effects more commonly in the literature. Again, 2 terms that mean the same thing. But a word of caution here. These are simple effects. When writing about these lower order terms, the phrases main effects and average effects should be avoided because they're inaccurate, they're misleading, they're wrong. Okay, be blunt about the wrong, don't do that. The term main effect comes from ANOVA, and one of the differences between ANOVA and regression is the way that the categorical variables get coded. In ANOVA, you tend to see effect coding, which leads to the term main effect. In regression, you see dummy coding, which is that 0-1 coding, which leads to simple effects. So just a point of clarification, when you're in regression, think simple effect. So let's get to the interpretation of the interaction term, even though it's not statistically significant. This coefficient describes how much the difference in the outcome variable, which is opinion here, between two cases that differ by 1 unit changes as B covar changes by 1 unit, and vice versa. And the reason it says vice versa is because remember that the interaction is symmetric. So you can simply switch the name binary var here and B covar here, and the sentence is still accurate. Okay. Because that even in the simplest case, that's a little bit to get your head around. Most people prefer those graphs, and that's why we're here for process. This is the graph of the interaction. We talked about this. So we're up to our first exercise here, and we've got 3 questions. I am going to give you about a minute to think about these questions, and then I would like people just to unmute yourself and give me answers to any question that you would like to answer. Okay, so we'll give you approximately 1 minute, and then we will come back and talk about this. All right, who would like to answer the question, what is the difference between a dichotomous variable and a binary variable? Go ahead, unmute yourself. I can't see the chat, so if somebody's typing in the chat, I'm sorry, I can't see it. If somebody wants to read an answer from the chat, that would be great too. But what's the difference between a dichotomous variable and a binary variable? This is important.
Oh, binary is 0-1. So 0 is the baseline and 1 compares it. And dichotomous just means 2 levels.
Perfect. Absolutely. Now, why would this matter in a regression analysis?
Because it's easier to interpret the 1 as compared to the 0. So if it's male, female, and it's positive, it means that men are higher, right? I think if men is 0 and women are 1, you multiply it by 0 for men, that's the baseline. And then women are multiplied by 1, so women are higher. And if it's negative, men are higher. So it lets you, it tells you, gives you information, more information than coding them in 1, 2. I hope I explained that right.
Yep. Now, a lot of software programs, when it sees 1, 2, at least if you tell it that it's a categorical variable, will switch it back to 0, 1. Let me ask you, in a regression analysis, what coefficient, the coefficient for what term is going to be impacted by coding a variable 0, 1 versus 1, 2. There's one coefficient that's going to be impacted. What is it? Okay, think about our definition of our constant or our intercept term. That is the expected value of the outcome when all the predictors are held at 0. So if you code your binary, your dichotomous variables as 0, 1, making them binary, 0 is now within the range of your predictor. If you've got it coded 1, 2, now 0 isn't a plausible value. Not that most people get excited about interpreting the intercept. I understand that, but that coefficient will change based on that. All right, last question. Given that an interaction term in your model is not statistically significant, what should you do? Does it stay in? Do you take it out? What do you do? And honestly, we get this question in consulting all the time. Okay, so definitely on lots of people's minds. Tell me, what do you do?
I'll answer because nobody else is. I would pull it out.
Okay, why?
Because it is adding, it's taking away my degrees of freedom. And so my other variables have less power.
Okay, okay. What we typically say in consulting is that you can go either way on this. If your interaction term is testing an important hypothesis, then you probably should leave it in because that's the test of your hypothesis. If you were just kind of snooping your data, looking to see what was there after you've done all of your hypothesis testing, then you're right, maybe you take it out because it certainly is going to ease the interpretation of the lower order terms. Perhaps not so much in this binary by binary example, but when we get to other types of interactions, then yeah. All right, let's go on here. SPSS keyword with. Notice the change to the reference groups. I got the output right there on the next slide. Here we have a with instead of by. Notice that the EM mean subcommand and the plot subcommand has been omitted. And here, corrected model, you see all of the same p-values that you saw before, but now you see that these match because both of them are using 0 as the reference group. Choice of reference group is completely up to the researcher. The fact that SPSS uses the highest numbered category is in no way wrong or inaccurate or anything. It's just a preference thing there. Although I do wish SPSS would let you change the reference group, but so far my request for that addition to the software has gone unheeded. All right, let's rock on here and talk about the binary by binary interaction with process. Here's what our syntax looks like. We have process here, of course, no surprise there, you got to give the command name. Y equals, and here is our outcome. Here is the slash. Like I said, you could have it all out on one line or you can have it down on multiple lines here. We use X to specify one of our predictors and W to specify the other predictors. The last two subcommands here are where the real magic happens. You have to know the model number, and the only place you're going to find the model numbers is in Hayes's book, and he did intend it to be like that. So
is Christine frozen on other people's screen?
Yeah, I can't hear her either.
Okay, let's give her a minute to come back.
yes, if you uncheck the, huh? if you, see here, I don't have SPSS up and running yet. I had to reboot. Let's see, take a while to come up. So you get this graph here. If you're just using it for your own purposes, that's perfectly fine. But for publication quality graphs, you may want to switch over to GPL. So the difference is that the syntax that Hayes gives you uses the oldest of the 3 graph commands in SPSS, which is the graph command. In the point and click dialog, that is under graph, and then down at the bottom it says legacy dialogues, and then you get that. If you want to use the newer graph commands, that's at the top, and you say graph, and then it will say chart builder. And chart builder uses a let's see here, let's open both of these up. Okay, there we go. So we got that. So here under chart builder, this is going to give you the ggraph command with GPL. And so GPL looks like this, and it's a double-edged sword. There's lots of control, but it is really persnickety programming, and worse, it's very un-SPSS like here. So this part up here, this that is SPSS syntax. So this could have been in lowercase, this can be in lowercase. Whatever you call it, the name doesn't make any difference there. You do have to have the correct variables listed here, and then you just leave this alone. But this begin GPL to end GPL, and that's the graphic programming language there. That is all case sensitive, and the order of the statements matters. So you've got to be super, super careful there as well. So I have some examples here. I put in opinion, put this here so the opinions on the name of the axis as well. Same thing here. This unit equals unit category here tells you that it is a categorical variable here. We've got some labeling done here. And then these element statements are putting the lines and dots on the graph here. And so we have shaped it, given it shape, and then the same thing for the lines. And you can change color, and you can do all sorts of things. And I really wish that it hadn't crashed, because I had that all up. So that's that. And then oh boy, my internet could be spotty again. Anyhow, when this comes up, what you're going to see is that I did write an extensive page on using GPL to modify the color of the lines and the pattern of the lines. And that's important because when you're publishing, you usually want black lines with different patterns. And so, and then SPSS has their own documentation on that as well. The one thing I will say about the SPSS documentation on GPL, which I find to be super annoying, although I know why they did it, the code that they give you is just a fragment of the code that you need. And so you got to kind of understand the whole thing. And then they're just giving you little snippets of the code in there. So there's that. GPL is very similar to the way graphs are made in our using ggplot2. So any questions before we move on to our binary by 3-level interaction section? Okay. So here we go. We're going to do this using the SPSS GLM command. We have our data set activate to make sure we're working on the correct data set. And especially as you start copying and pasting the code from the process output, you will start getting more and more data sets open. So this data set activate thing is going to become more and more important. We have the GLM command. Opinion is our outcome. We have by. Our binary variable here, and then this is detail 3, which is our 3-level variable for detail. Our design, we have our lower order effects here, and then our interaction term here. Print equals parameter to get the regression coefficients in our output. We can still use EM means because all of our variables follow the SPSS keyword by, and then we have our plot to get us that. Our output is going to start off looking like this. We see that our overall model is statistically significant, but the interaction term is not. Now, some people get real excited when one of the lower order effects is statistically significant. That doesn't really do much for me unless that one specific comparison was of interest to you based on your own research questions. But in general, I don't care one way or the other if the lower order effects are statistically significant or not, but they must be in the model. You can't get rid of them if they are not statistically significant, that those things have to stay in there. Here is our, oh, the other thing I was going to point out here. Notice this is our 2 degree of freedom test here, which, like I said, is really handy. So you know, overall, the variable is a statistically significant predictor of the outcome, as opposed to what you get in this table, which is a comparison of 0 to group 2, and then a comparison of group 1 to group 2. So these are 1 degree of freedom tests in this table, but it doesn't tell you if overall the whole variable is statistically significant. And obviously you can't tell from the p-values given in this table. Here, we get the EM means output here, and then we get our graph here. And you can see why the interaction isn't statistically significant. You especially look here at these error bars. I mean, these error bars are huge. And so even if the interaction isn't statistically significant, a lot of folks still go ahead and graph them because they want to see something like this, because it gives you some indication of what is going on. So when binary variable equals 1, there seems to be a lot of variability here. And, you know, that may be informative in your research, but it tells you what's going on there. Here's the process code for this. Again, we have our data set activate here. Process y equals opinion, x equals binary var, w equals detail 3. Notice our new subcommand. Why do we have a new subcommand? Because we've got to tell process that detail 3 is a multi-categorical variable. And so that's, and the 1 just means to turn it on. That's the way Andrew Hayes does it. So equals 1 means turn it on, turn it on. That's what those 1s means. But our W variable, W multiple categorical here. And there is obviously MCX and even MCZ if we had a Z variable there. So you do have those subcommands to let process know that these are categorical. Now, interestingly, Hayes chose to use 0 as the reference group. So when you're using process, 0 is going to be the reference group, not the highest numbered category like is typical in SPSS. So you need to pay attention to that. Here's the process output here. I always ask people to look at that top part carefully. And the reason I want you to look at that top part carefully is because it ensures that there was clear communication between you and process, right? If this part doesn't look right to you, then you need to stop and go fix things. So I understand that it's easy to blow past this and try to get to the coefficients, because that's what you came here for, right? But just stop and make sure this is okay. And then you want to look here. This tells you that detail 3 equals 0 is your reference group. When detail equals 1, W1 equals 1, and when detail equals 2, W2 equals 1. And so that tells you how the variables were coded. There are other potential coding systems that you can use. I don't go into that in this workshop because they're not used all that frequently. But if you didn't want dummy coding, you do have other options. For most of the rest of this, I'm going to stick with the PowerPoint because since I had to reboot my computer, I had to close down SPSS, of course, and now I have to go back and rerun process to run everything, and we're running out of time. So I'm just going to stick with this. I do apologize for the inconvenience there. Our model summary here, this is again your test of your overall model here. So the test of the model is an F test, and this is your test statistic on 5 and 194 degrees of freedom, and the overall model is statistically significant. Here is your constant, your coefficients here. The indication of what this means is right down here. So int underscore 1 is binary var times W1, and we found out what W1 was right here. So that is when detail 3 equals 1, and then int 2 is this. So this interaction term has 2 degrees of freedom itself because detail 3 had 2 degrees of freedom. And that test of the overall interaction is right here, and we see that it is not statistically significant. Here's the 2 degrees of freedom here, and again, the 194 matches this. Okay, so at the very bottom of the output, what you see is this, and you double click into the output from process in the output viewer, and you just copy and paste this into your syntax. In your SPSS syntax, it's going to, let's see here, it's down here, it's this one here. And you just copy and paste it in here, and you highlight it and run it the same way that you would highlight and run any other code in SPSS, and you get this. The dots aren't so informative, so double click in here, come to elements. I think you can still do fit line here. Make sure you uncheck this attach line to label to get rid of these things, because you don't want that hanging out there. Just close this. And then when you close this, now you've got the lines drawn on here. There's minimal modification that you can do to this kind of graph. And so for showing yourself what's going on, your lab mates, your research team, this is perfectly fine. For publication, probably not so much, which is why I wanted to introduce the GPL. All right, so that is just a picture of that. I promised you that the slides would go pretty quickly. The try it yourself, I'm going to skip past this just in the interest of time, but the text file that's linked on the web page there has the answer to this, and I did tell you the answer to that, so if you happen to remember back a few minutes, you know what that is. And then just rewriting the syntax. It's not nothing to write home about. Okay, binary by continuous interactions. Your SPSS GLM syntax is going to look like this. I've used with because age is continuous, and I just left binary var there. It's 0, 1. I can use it after with or by, and I don't see any reason to use by here. Once I got age into this, I lost the ability to use em means or the plot subcommand. So let's just stick with this. Here's our design. Lower order effective age, lower order effective binary var, and their interaction. we get an output that looks like this. Our overall model is statistically significant, and so is our interaction this time. So finally, something to talk about, right? Here are our parameter estimates here. Notice the p-values match what we saw up here again, because there's no change in the coding. Interpretation, overall model is statistically significant. It's misspelled. Okay. Yeah. Statistically significant. The intercept is this value, which is the expected value of the outcome, which is opinion, when all the predictors are equal to 0, whether that is realistic or not. In this case, it is not realistic because age doesn't take on the value of 0. So again, report the intercept, don't bother interpreting it. The coefficient for age is 0.733, and this is the effective age when binary var equals 0. Again, because we use the SPSS keyword with. It is a simple slope. When you have continuous variables, they talk about simple slopes. When you have categorical predictors, they talk about simple effects. It's the same idea. The coefficient for binary var is 31.319, and it's the effect of binary var when age equals 0, even though that's not a value in the data set. And this is a simple effect. And then the interaction term shows how much the difference in opinion between two cases that differ by 1 unit on age changes as binary var changes by 1 unit. In other words, it goes from 0 to 1. And in the book, if you want to look this up and read the rest of the discussion on interpretation, look on pages 254 through 255. But that's the interpretation of this. And so you can see why it is that people might report this and then not go ahead and interpret it, because, you know, unless the effect of well, this one doesn't do you, age doesn't do you any good, or this one might do you, excuse me, might do you some good here, because you can look at the effective age when binary var equals 0, but the effect of binary var when age equals 0 doesn't make any sense. And while you certainly can interpret this, I could see where, you know, it's a little bit difficult to write about. Your process command looks exactly like you think it's going to look. We have Y, we have X, we have W, we have model 1, we have plot 1. Everything is just the way that you would expect to see it. The output, again, is going to look very much like you expect. We have the overall test of the model. We have 3 degrees of freedom here. The overall model is statistically significant. Here are coefficients here. Int 1 is the interaction of age by binary variable. And this number here is this number here, because they're just 2 ways of doing the exact same test. What we do get here is some additional output because the interaction term was statistically significant and we had a continuous variable in the model. And so we get this here. What we see is the effect of this is the predicted value of age when binary variable equals 0, and the predicted value of age when, excuse me, of the outcome, I'm sorry, opinion, when binary var equals 1 here. Do not get excited about the rest of this. This is not something that I would report or get worked up over. All it tells you is that 0.7 doesn't equal 0, and it's possible that 0.17 does equal 0. So these aren't really interesting. Your p-values should come from this table up here, not from here, but those are values that you will see in the graphing. And in just a moment, I'll show you where all those values come from. This is the syntax that process gives you in order to graph the interaction. And when you graph the interaction, it comes out looking like this. And again, nice crossover interaction. It's statistically significant. I would still like to see the error bars on it, but that's what we get. And then we have these 3 dots here. So how are those values of age calculated? Where did those values of 41, 54, and 62, this 41, 54, 62, this is the value of age. So this is age. These are the values of this. These are the values of opinion. Where did they come from? By default, Hayes uses the 16th, the 50th, and the 84th percentile to calculate those expected means, estimated marginal means, least squares means, whatever you want to call them. And he does that because it ensures that they will all be within the range of the variables. Sometimes, especially with very skewed variables, if you take the mean and 1 standard deviation above or below, you might exceed the range of the data in the data set. And of course, that's a problem. And so if you use these percentiles, you're guaranteed to stay within the range of the variable. The other thing is you don't usually want to get way out to the extremes, because usually you have less data at the extremes and the error bars are really big, and things start to get a little bit dicey. So staying closer to the bulk of the data gives you more stable estimates, a better idea of what's going on. In SPSS, if you say dataset activate and you use the frequencies command, which I have shortened to freak, you can shorten any of the SPSS command names. I've asked for the variable age. I asked for the median, which of course is the 50th percentile. And then I use the percentile subcommand for the 16th and 84th percentile. And I just said no table to get rid of all the rest of the output. This is what you get. Here is your median, which is that 54. Here's the 16th percentile, which is your 41, and your 84th percentile, which is your 62. And that's where they came from. Okay. How were the values of effect calculated? So we were over here and we saw this 0.73 and this 0.17. Where did those values magically come from? So the effect here is B1 plus B3. So that's what effect is. So B1 was the coefficient for age, and then B3 is the coefficient for the interaction term. And I just copied those numbers off of the output. And then when you do this, you just add like it says here, but this is when binary var equals 0. So this is 0. So all that goes away and you're just left with the coefficient. This is a subtraction because this is a negative coefficient. It's multiplied by 1. So you just do the subtraction. And that's where those numbers came from. So I just wanted to show you that there's no magic, no black box, no nothing. That's where those numbers come from. Later on, I will show you how to override that default of using these percentiles, and you can use the mean and plus and minus 1 standard deviation if that is of interest to you. Continuous by 3-level interaction, we're going to boogie through some of this stuff. GLM opinion with age by, I've got to use by now because this can't be treated as continuous. The design subcommand is exactly what you expect, and then we have our print equals parameter. We see the 2 degree of freedom test here for detail equals 3. Our overall model is statistically significant, but our interaction term is not. Okay, looking over here, again, we've got our coefficients. The highest numbered coefficient, the highest numbered level here is the reference group for the lower order effect, as well as for the interaction here. So the process code, Y equals opinion, X equals age, W equals detail 3. Remember, now we have to use our multi-categorical W subcommand to tell process that this has more than 2 levels. model equals 1, plot equals 1, and now we have int probe. So int probe is used because by default process only probes statistically significant interactions, which in a research situation makes a lot of sense. But if you're just trying to get a handle on what's going on, Hayes gives you this way of looking at a statistically non-significant interaction, and you can go ahead and look at that using this int probe equals 1. So here's part of the process output. I skipped over some of it just because I already had 140 slides. We've got our key here to tell us what these product terms equal. Again, we see that the interaction term is not statistically significant, but this part of the output is there because we use int probe equals 1. And so we see that we have our 3 values of detail. Effect is calculated as we just saw. And then when we come over here, we have our graph command that we simply highlight, copy into our SPSS syntax in the next queue. All right, that's what the interaction looks like. Looking at that, I'm not surprised that the interaction isn't statistically significant because those look like 3 parallel lines to me. All righty. Boy, what happened here? The intercept here is statistically significant. Who cares? When all the predictors equal 0, whether it's realistic or not. The coefficient for age is 0.4716. It's the effect of age when details held at its reference group. In this case, that is held at 2 because it's coded 012. The reference group is different in GLM and process. It is still a simple effect. The coefficient for W1 is 6.7582. It's the effect of W1 when compared to the reference group when age equals 0, simple effect, and the same thing here. Interpretation for the interaction terms here shows how much the difference in opinion between 2 cases that differ by 1 unit on age changes as detail 3 changes by 1 unit. The coefficient for the other term has exactly the same interpretation. So that's how you can interpret those coefficients if that is something you want to include in your manuscript. Continuous by continuous. All right. The syntax is exactly the same, no surprise there. This looks exactly the same. And we see here that the overall model is statistically significant. We've moved into the exercise data set. So we're using the exercise data set, and that's why here the outcome is loss, X is hours, and W is effort. These are, of course, continuous predictors here. And we've got our coefficients here. There's only one interaction term because it's only 1 degree of freedom. So we have that. And then the interaction term is statistically significant. No surprise there. Okay. So now we get to this, and there are values of effort. Again, these are the 16th, 50th, and 84th percentiles. We calculate this value as we saw above, and then we get this part of the process output, which we can graph in SPSS. Oh, and this is the last part of the output, and I included this just because now you have this additional line here telling you that W is equal to the 16th, 50th, and 84th percentiles, just so that that note is there. You don't have to just like magically remember it. It's in the output to remind you. And we get this graph here, and you can kind of see that the lines are not parallel there. So that's cool. Let's see here. The coefficient for hours is this negative 9.3757. It's the effective hours when effort equals 0. The coefficient for effort is this minus 0.08, and the effective effort when hours equals 0. And these are called simple slopes. And then look at page 302 for more information. The interpretation of the interaction term shows how much the difference in the outcome variable loss between two cases that differ by unit on hours changes as effort changes by 1 unit. So that's what it means. Now, when we're in a continuous by continuous interaction situation, Hayes calls his 16/50th and 84th percentile the pick-a-point approach to probing the interaction. The alternative approach when you're in a continuous by continuous situation is the Johnson-Neyman significance region here. You get that, and it's just in addition to the output. There's no addition to the plot. I wish there was, but there isn't. And that's this JN equals 1 here. And this is what is added to your output here. So that's all you get. If you want to use the mean, 1 standard deviation above and below instead of the percentiles, that the mean and standard deviation are known as moments, the first and second moments of a distribution. And so that's why he calls it moments, and you can use this moments equals 1. And then you will see that we're using different values here. And then we talk about how they got calculated here. If you have the means command in SPSS and var equals effort, here is your mean and here is your standard deviation. So here's -1 standard deviation, here's +1 standard deviation. So that's where that 24, 29, and 34 are coming from. There's the 29, 24, 34. That's where those numbers are coming from right there. We did that. You can also provide your own values if you would like to, with the W mod value here. You can put them in, do separate them by a comma. And I just picked kind of something that looks low and something that looks high from the data set. And then you see there's the 15 and the 40 that I specified there. And then in the output, you see the 15 and the 40 here, and you graph it. I only have 2 lines because I only picked 2, but you will see they look pretty much the same thing as you would expect. If you want to make the graph look nicer here, I threw in some GPL syntax. So you've got that you can use. And here you go. And again, you can modify the color of the lines, the pattern of the lines, the different shapes. You can get in here and modify the way that these are labeled and do all sorts of stuff. Okay, a couple models before we finish up here. There's a two-way interactions, what Hayes refers to as additive multiple moderation. And the conceptual diagram looks like this. We have X predicting our outcome Y, and W modifies that relationship. We've seen this before, and now Z modifies it as well. The statistical model looks like this. We have X, W, and Z predicting Y, and then the 2 interaction terms also predicting Y. The SPSS GLM syntax for that looks exactly like you would expect that it's going to. what you need to be careful of here is making sure you've got in all your lower order terms, right? Because SPSS won't tell you that you have forgotten a term because it thinks that you specified whatever model you intended to. It doesn't think you made an error. So on this design though, and when we get to the next model in particular, you've got to make sure you've got all your terms specified here. Your output's going to look like this. Our overall model is statistically significant. One of our interaction terms is, and one of our interaction terms is not. And then here's our list of coefficients that we get. The process code for this looks exactly like you think. We have a Z subcommand here for our third variable. And most importantly, we have switched from model 1 to model 2. Do not ever get the wrong model numbers because it doesn't work and you get a whole bunch of strange gobbledygook. So we're in model 2. Model 2 is the one that has the 2 interactions in there, but no three-way interactions. We use the int probe equals 1 because one of the interactions was not statistically significant, and then we still ask for the plot. The process output's going to look like this. We used model 2. Here are our variables. Our sample size is 900. Again, the overall model is statistically significant. Here are our 2 interaction terms here as we expect. And then the tests of the interactions, we saw these 2 numbers in the SPSS output. This is a test of taking both of them. So 2 degrees of freedom, 1 degree of freedom for this interaction, 1 degree of freedom for this interaction. Taken together, the 2 are statistically significant. I don't know if that's important to you or not. That'll depend on your research question, but it isn't something that you would have gotten out of SPSS GLM. Okay, so we've got values of effort because we didn't tell process otherwise. This is the 16th, 50th, and 84th percentile. For the one variable here is the female 0 and 1, and then our effects. And then this is what it looks like for the graph command. So we're going to enter the data set here and the data set, and then the graph. Couldn't get it all on one slide. And then again, our reminder about the percentiles. And then this is what the graph comes out looking like. So it's broken out. This is female equals 0, and this is female equals 1 here. So if that's the graph you want, that's great. I don't know, but that's all you can get out of process for that. For our interpretation, the coefficient for hours by effort, or int1, quantifies how much the conditional effect of hours on loss changes as effort changes by 1 unit holding female constant. For the other interaction, this coefficient here estimates how much the conditional effect of hours on loss changes as female changes by 1 unit holding effort constant. And again, look at page 339 if you want more on that. All right, three-way interaction, or what Hayes refers to as moderated moderation. This is what the model looks like here. So we're familiar with W pointing to this arrow here indicating an interaction. Now we've got Z coming in here to moderate this, and this is where the moderated moderation comes from. Your statistical model looks like this. You've got the lower order effects of X, W, Z, all of the two-way interactions, which is WX, XZ, and WZ, and then finally the three-way interaction of X, W, and Z. You'll have to look at that, the answer there. Just remember how SPSS handles the coding of categorical variables, and that'll help you out with that one. Okay, so this is what the process code is going to look like. Loss is our outcome. We have hours, we have effort. Z is female. Notice that we've moved to model 3. Critical thing to note that we are now in model 3. So we're in model 3. We've got this. This output should seem familiar by now. We've got the overall test of the model, our coefficients, and then our cheat sheet down here. I couldn't fit it all on one slide without it being microscopic. So int 4 is the three-way interaction. The three-way interaction here is not statistically significant. Okay, so that's what you're seeing here. And for that matter, none of the interaction terms are statistically significant. So we've got that. Here's our process output for the graphing, and then there's our graph there. Interpretation. Okay. The regression coefficients for products involving X in these types of models quantify the rate of change of X's effect on one moderator as one moderator changes when another moderator is held fixed in the additive multiple moderation, or as another moderator varies, which is a moderated moderation. So that's the interpretation difference between the two models. And you can see why people might want to shy away from interpreting that. Go ahead and give that a try at your leisure. I don't know which graph you're going to like better. That's going to be your choice there. A couple of options that I want to talk about before we wrap up here. Adding covariates to the model is easy. You use the cov subcommand. You can add continuous or binary variables, but these, if you have something like detail 3, you're going to have to dummy them before you put them here, but this is what you're going to get here. And then here I just put this here so you see that it adds the covariate, and it adds the covariates here. If you want heteroscedastic standard errors, then you want to use this HC 4. 4 is the default in SPSS, but I believe it actually has 5 options there, but you can use this to get that. And when you look, whoops, when you look here, you will see where I've bolded it, that it's using the heteroscedastic standard errors there. One last thing, and I always find this to be an important thing, how to change the number of decimal places so that you don't have to sit there and round everything to whatever. You use the decimals subcommand, but it really has to be F and then however many spaces. .2 says I want 2 places here. So if you look at your output here, notice everything is now down to 2 decimal places here. And the same is true when you go to graph things. Not a big deal with respect to graphing, but quite the convenience when you need to go to report some stuff. Another try it yourself here. We can discuss that in just a minute if we don't have any other questions. And then the last slide, I wrote down some of the useful pages in Appendix A because they don't show up in the index. And I found that to be like totally frustrating. So the syntax diagram, so, you know, the whole list of all the different possible subcommands and subcommands and their options. That syntax diagram is on page 581. It's in Appendix A. The diagrams of all the models starts on page 621. The coding systems for multi-categorical variables X, W, and Z is on 594. And there's some other stuff in there. This part here, if you've got the book, definitely read these notes here because it gives indications of when process may not work or some other issues that you might be aware of there. Oh, and 611, as in SPSS, not all of the options and process are available through the point and click interface in process. And so that's another reason why you may wish to use the syntax, besides the fact that you want a nice written record of your work, but that way you can use all of the options that are available to you. All right. Again, I apologize for my connectivity problems. I would like to open the floor now for any questions. Is anybody still there?
I'm still here.
Oh, good. Thank you.
Yeah.
Does anybody have any questions? Hi, thank you. Thank you for at least letting me know you're here. Any questions?
So I asked Andy this. I already have the first two of Hayes' books. Has it changed significantly enough? I know, M+.
Oh, yeah, you're right. Hold on here. Let me see here. I got the book. I got the book right here. And I know what you mean, because I've got the first two of Hayes books myself.
Right.
I do know that. Let me see here. What was added in here?
Someone said R was added.
Yes, that was one of the major things that got added, was all the stuff about R, because he did write that. Here we are. What's new in the third edition? The new edition is a bit longer than the second edition, but only slightly heavier. Sequence of chapters is consistent with the second edition. Vast majority of the material of the second edition has been retained. Yes, most of the pages are a bit different. Most significantly, the result of adding syntax support for R users and the new release of Process for R. Other changes include the addition of new sections throughout the book. The R code, he rewrote Appendix A to reflect the new features added to Process since the second edition, including a discussion of similarities and differences in syntax structure for Process in R compared to Process for SAS and SPSS. More detailed discussion of effect scaling and the difference between unstandardized, completely standardized, and partially standardized effects in chapters 3 and 4. A rebuttal in chapter 4 to a claim made by some researchers here that we should return to a test of joint significance rather than rely on bootstrap confidence intervals about indirect effects. New discussion in chapter 5 about the method for comparing the strengths of two specific indirect effects that are different in sign. And some other things. So I don't know.
Okay. I don't need R, so I will chance it without it for now.
Understand that. You're a Stata user. No, he doesn't have anything for Stata, because in Stata, the whole thing would be done through the SEM command. And so there really isn't a need in Stata for or in M+. M+ can run all of these models. There's no need for Process here. You could run most of these models in SAS, but it would be pretty difficult. And so Process was implemented in SAS to make this easier. It's implemented in SPSS because SPSS doesn't do mediation. It doesn't. If you wanted an IBM product that did that, you would need to move over into Amos. So that's why it exists here. In in R, there are lots of packages that would do this, but again, he's trying to make it user-friendly, and some of the R packages that will run these models are not what most of us would consider user-friendly. So, but they're really not needed for Stata or M+. The native commands will run these models. Both SPSS, excuse me, both Stata and M+ will actually make the diagrams. You know, if you've got a mediation model, it'll make the diagrams for you. It's really sweet stuff. So he was filling a gap with some software, and that gap doesn't exist in all the software. Let's see here. Let's see here. There is no multi-level modeling available through Process. No. It is available through M+ and through Stata, and I'm pretty sure in one of the R packages, but it is not available through Process. For that matter, neither is handling complex survey data, so no weighted data, nothing like that. Process doesn't handle that. There's a feedback link that Andy put in the chat. If everybody would please do us a favor and click on that and fill out the short survey, we would appreciate that. Again, I do apologize for the internet connectivity issues that occurred. Any other questions that I can address at this time for anybody? Someone asked about the Johnson Neyman test. Yes, that is called the floodlight as opposed to the spotlight, which is the pick-a-point approach. I love the term spotlight and floodlight. I just think that they're totally humorous. They're basically different ways of kind of doing the same thing. Some people have preferences for one or the other. I personally do not. I have seen presentations of the graph of the interaction with the Neyman-Johnson region, either shaded or something like that. But really it's, I would say it's the researcher's call on that. Okay, what other questions do we have? I don't expect any criticism for using Process. You know, Hayes was very careful in programming this. He tested it against programs like Stata and M+. So I would not expect any pushback about using this macro. Goodness knows he has tested it against a lot of other software. So I think he's I think you're good to go there. As long as you're staying within the realm of what Process does, and that is a fairly defined realm, but if you're within that realm, it's all good. Okay, any other questions that that I can address? Everybody has the link to the survey?